Footstep-driven power generator. This project uses piezoelectric elements, which are hidden under the platform that says step here, and every step generates a little bit of voltage, which goes through circuitry to charge a 3.7 volt lithium-ion battery. The leftmost wires are connected to the ground and power of the piezoelectric platform. The next two are the power and ground after voltage gets purified to a level where it's safe to charge a battery. The next terminal block connects the battery with a 0 in the Arduino for voltage reading. The two wires after that are connected to an external power and ground to power the Arduino and LCD, as powering it purely on the battery would be inefficient. Finally, the last wire is the lithium battery's ground, which is connected below the PCB, and there are also holes on the sides of the 3D case so wires can pass through from one side to another, which is what the wires on the two sides of the project are, as you can see here. Here I am stepping on a platform, and on the right I have live footage of the device showing the voltage of the battery. It takes nearly 3 minutes to generate even a small bit of voltage, so it is fast forwarded until the last 5 seconds. Here you can see that the voltage of the battery has increased by a small amount. So now, let's talk about how it works. Once the piezo element is pressed, the mechanical compression or tension on the piezoelectric ceramic element, it changes the dipole moment, and that is what creates a voltage. So in an ideal case, the more pressure you add, the more voltage generated, but it isn't perfectly linear because the rate of the voltage increase is not always constant, and this behavior is due to the piezoelectric material's inherent properties, such as its capacitance or the way it deforms under stress. So when choosing the optimal material and size, I use a quartz variant as they are the most widely used, and after experimenting with multiple sized piezos, I found the general trend that the larger it is, the more voltage it generates, thus I used the 50mm ones as they are the largest that I could find. It is also important to find the resonance frequency of the piezo element to ensure it's well above the max voltage frequencies. For quartz, I used a piezo that has a resonance frequency of 700 Hz, and through the graph, quartz generates the most voltage at 610 Hz, so the resonance frequency of my piezo is well above the frequency that gets me the max volts, which is important for optimization. If it's near the resonance frequency, every time it reaches that frequency, it won't actually get to the max voltage, and rather it will just damage the piezo. So that buffer is always good to have. The AC voltage generated by piezoelectric elements is unsuitable for directly charging a battery or powering electronics, as it alternates between positive and a negative cycle. To convert this into usable DC voltage, a bridge rectifier made of 4 diodes is used, and the diodes are arranged to allow current to flow in only one direction, effectively flipping the negative half of the AC sine wave to positive, and during each half cycle, 2 diodes conduct, ensuring unidirectional current to flow. This rectification process eliminates the negative portion of the waveform, making the output suitable for storage or further regulation. After the AC voltage from the piezoelectric elements is rectified into DC, it is still unstable and prone to fluctuations, so to smooth out those ripples, the voltage passes through a capacitor, which stores and releases charge to provide a more consistent DC output. This smoothed voltage is then fed into a 7805 voltage regulator, which maintains a steady 5 volt output as long as the input remains above 5 volts. If the input drops below 5 volts, it is just not used for charging. It won't go through. The regulated 5 volt DC is then routed to a TB4056 charging module, which safely just charges a lithium-ion battery using constant current and constant voltage methods. So the TB4056 ensures efficient charging while preventing overcharging and protecting the battery health. Here's the code used to display the voltage onto the LCD. Thank you. This Arduino program reads the analog voltage from pin A0, converts it to a real voltage value assuming a 5 volt reference, and displays it onto a 16:2 LCD screen. It continuously updates the second row of the display every 500 milliseconds with the current voltage reading. Thanks for watching.